In this video, we want to find the Taylor or Maclaurin series of each of the following functions by using one of the series in the table, and then determine the interval of convergence. Well, actually, for the first one, I am not going to use any of the series in the table. I decided to go through this one using the entire process for developing a Taylor or Maclaurin series. So first of all, because it is centered at 0, we are looking for a Maclaurin series. And the first step in this process is to find the Maclaurin polynomial. And so a Maclaurin polynomial has to involve a function with an infinite number of derivatives. And so we start off the process by finding the first few derivatives. And so, as I've showed you in other videos, I like to do this in a methodical way. So I start by writing out the function and then evaluating that function at a equals 0, which is 5. Then finding the derivative of f of x. And again, I'll leave it up to you. These are very easy derivatives to find that derivative. And then evaluating that at 0. Now you'll notice I'm doing something peculiar. And that is I'm not just multiplying, 2 factorial is 2. I'm just not multiplying the 2 times the negative 5 and getting negative 10. I could. This would be negative 10. But I'm going to want to look for patterns. Remember, everything that we do with series involves patterns. And so you're going to see a pattern developing here. Then the second derivative, and evaluated at 0, I get 5 times 3 factorial. The third derivative, evaluated at 0, I get negative 5 times 4 factorial. And so here is my Taylor series formula. And the first term, f of a, is just 5. The second term is f prime of a, which is negative 5 times 2 factorial times x minus 0, which is just x. The third term is f double prime of a, which is 5 times 3 factorial times x squared over 2 factorial. And then we have minus 5 times 4 factorial times x cubed over 3 factorial. And so simplifying that, we end up with the first term. This is the second term. And again, I'm not multiplying the 5 times the 2 yet because I want to look for some patterns. 5 times 3x squared, 5 times 4x cubed. So what we need to do is we need to develop from the Maclaurin polynomial, we need to come up with the Maclaurin series representation for this. So we see that we have a 5 in every term. Basically, I just factored out that 5 to get rid of it. I see that I have an alternating series starting with a positive term, negative, positive, negative. So I'm going to have a negative 1 to the n. Then what I'm left with is this and this and this for each term. And so starting at n equals 0, this is n equals 0, this is n equals 1, n equals 2, n equals 3. And so for n equals 1, the coefficient is 2. For n equals 2, the coefficient is 3. For n equals 3, the coefficient is 4. So the coefficient is n plus 1. And then, of course, the power is n. And so there is the Maclaurin series representation for this function. So the next thing that we want to do is determine the interval of convergence. And so, of course, we've done this for power series before. Use the ratio test. And so using the ratio test, we want to take the limit as n approaches infinity. And so we have our a sub n plus 1 divided by a sub n, going through the usual process of breaking up the terms, canceling out the common terms. We end up with an x, which I bring out in front, times the limit of the n plus 2 over n plus 1. And so using our techniques for finding limits, you can use L'Hopital's rule, you can use the technique that I did here. We have lots of techniques that we've learned for doing these. We end up with the limit being equal to 1. So the absolute value of x times 1 is the absolute value of x. And in order for that to converge, it has to be less than 1. So that means that solving that absolute equation, we have x is less than 1 and greater than -1. And so therefore the radius of convergence is 1. Now notice all it said was determine the radius of convergence. Back up here. And it said actually find the interval of convergence. So I did not do that. So to find the interval of convergence, we have to test the endpoints. Okay, so that I did not do. We would need to go back into our power series, which is right here now. And we need to test for x equals 1 and x equals -1 to determine whether it converges or diverges at those points. And so I will leave that up to you to do. But the radius of convergence is r equals 1. Okay. And let's just do one more. And so in this one, I am going to use the table. I'm going to use the table for e to the x. In the table, we have e to the x is the Maclaurin series from 0 to infinity of x to the n over n factorial. And so that's what we have here. And so we're going to replace x with -2x. So replace x with -2x and break that up into -2 to the n times x to the n, as I did here. And then that would be our Maclaurin series representation. And if you wanted to, you could even factor out that negative from the -2. It's not necessary. Sometimes I'll do it -1 to the n times 2 to the n x to the n over n factorial. But in this particular case, I just left the -2 in there. And so using the ratio test to determine the interval of convergence, same old ratio test that we know and love from so many other times we've used it. And so we take this, all of this is my a sub n plus 1, and dividing it by a sub n, or multiplying by the reciprocal of a sub n, and then simplifying it, we end up with the limit of -2x divided by n plus 1, bringing out the -2x out in front, times the limit as n approaches infinity of 1 over n plus 1, and so we know that that is going to be 0. And so absolute value of -2x times 0 is 0, which is always less than 1. Well, what does that mean when it's always less than 1? That means our interval of convergence is infinity, and our radius of convergence is infinity. What this means is that this Taylor polynomial, Maclaurin polynomial, this Maclaurin polynomial that we have, and this Maclaurin series will converge for all values of x to e to the -2x. And again, you could use Desmos to see this. As we increase the number of terms in the Taylor polynomial, it's going to become a closer and closer and closer and closer approximation. And I believe that is the last one for this particular video. Actually, there's one more. Let's just do this one. I hope I don't have to redo this. Actually, I'm going to do this in another video because I'm worried about my video recording not working and having to do this all over again.